Hello, this is Math Jazz from Almost Cool, and we have today a live stream that deals with finite mathematics, basic set theory, and if we get around to it, maybe some probability. If you have any questions, then please send them to me in chat or email them to me at mathjazz9@gmail.com, and I will get around to answering those. Also, if you have any calculus questions, you can feel free to ask those as well. However, the questions I prepared today were on basic set theory. So, with no further ado, let us get to our questions. So, our first question of the day, we're just going to start slow and build up to some more difficult set theory questions. So, first thing that we want to do is review maybe a little bit of notation. We do this, so we want to check to see which of these statements are true or false. I'm going to write a bunch of statements here. There we go. So we have 3 is in the set 2, 5, 7, 9, 10. Have 9 is not in the set 2, 1, 5, 8. Have 3 is not in the set x such that x is even. And about x such that x is natural greater than 7 and less than 10 equals the set 8, 9. Okay, so we have these 4 different expressions, or these 4 different statements, and we want to see which of these are true. So, let's start with the first one. Is the element 3 in the set 2, 5, 7, 9, 10? The answer is no. This is false. This number 3 is nowhere to be found in this set. So this symbol here, it looks like kind of like an E, except that that part doesn't connect. This symbol here means in, or is an element of, whereas this one means is not an element. That's what the slash through the symbol means. So the expression 9 is not an element of 2, 1, 5, 8. This is a true statement. It's true because none of these numbers are 9, so 9 is not in this set. Okay, so we have 3 is not an element of x such that x is even. Well, that's true. 3 is odd, not even, so 3 is not an element of this set. This is true. And then our last statement, the set of elements x such that x is a natural number greater than 7 and less than 10 is equal to the set containing 8 and 9. Well, so this notation means that everything on the left side of the vertical line represents what an object's kind of generic characteristics look like. So it looks like some single number, as opposed to maybe being a list of numbers. That would be a perfectly reasonable thing to have as a set. A set of pairs of numbers would look like this, maybe. The set x, y, such that whatever. This would be a set where every element is a pair of numbers rather than just a single number. So x such that x is a natural number greater than 7 and less than 10. So what are the natural numbers? Well, they're the ones we use to count things with. So which ones are bigger than 7 and less than 10? Well, 8 and 9. So this statement is true. Okay, so that is question 1. And that reminded us, if we weren't already familiar with set builder notation, the element symbol and the not element symbol. Let's move on to a new problem. Okay, so how about we will define some sets right now. So we will say that the universe of our situation, universe that we're working with, will be the set 2, 4, 6, 8, 10, 12, 14. And we'll define 2 sets to start off with, and we might need more later. So let's have A be the set 2, 4, and B be the set of 8, 10, 12, 14. Okay, so given that these are our 2 sets, let's write out what A union B is, and let's say also A intersect B. Well, A union B is going to be the set containing 2, 4, 8, 10, 12, and 14, because union is everything that is in both of these, or everything in one set and everything in the other set. So we can think of it as being like a both. We say we want all the things both in A and in B. All of the things, we both want the things in A and the things in B. And then A intersect B is going to be where we take only the things that are in A and in B. So before we took things that were in A or in B. And the intersection is going to be the opposite. So these are the things that are in A and also in B. So 2 does not exist in B, 4 does not exist in B, and that's it. There's no overlap between A and B, so this is the empty set. The empty set is the set with nothing in it. We usually write it as this 0 with a slash through it, but we can also write it as just 2 empty braces because there's nothing in it. So that reminds us of what an empty set might be. Okay, so new sheet of paper. We will continue working with our set A and set B in the universe U, but let's add a few more sets to this to make it a little bit more complicated. So let's have a set C, which is going to be the set, how about 4, 8, 12, and a set D, which is going to be equal to, let's say, 2, 6, 10, and that'll be good enough. So now, let's do A intersect C. Well, A was just the set with 2 and the set 4 in it. C is the set with 4, 8, and 12 in it, so the only thing that's in both is 4. So A intersect C is 4. And let's do D minus B. So this notation means we take all of the things in D, all of the things in D, and we delete the ones that happen to also be in B. So we look at D and we see this is 2, 6, and 10. Now 2, when we look back at our definition of B, is not in B, so it gets to be in our difference set. 6 is also not in B, so it gets to live in there too. But 10 is in B, so we delete it, and that's the last element of D, so we close off our set. So D minus B is 2 and 6. And if you're wondering, well, what happens to 8, 12, and 14? They were in B as well. Well, they don't matter. Set subtraction is different from regular subtraction. In regular subtraction, you can go negative if you're subtracting more than you start with. But in set subtraction, you can't. You either were in the bigger set, in this case D, and you get deleted, or you weren't and you don't matter. So let's see, we have our intersections, we have our unions, we have our set subtractions, we talked about the empty set. Let's work on complements now. So let's say, what is C complement? Sometimes written with a superscript C like that, or sometimes written with a prime. Both of these mean complement, depending on the textbook you're working out of. Okay, so the complement is everything that's in U minus everything that's in C. So that's the complement of C. This is the definition. And what is that? Well, let's look at U. U are the even numbers between 2 and 14. So we don't need to really look at them very heavily. We say, well, what's in C? 4, 8, and 12. So what are the even numbers between 2 and 14, including 2 and 14, that are not 4, 8, and 12? Well, 2 is one of them. 4 is not. We delete 4 because 4 is in C. 6 is in the set. 8 is not, because 8 is in C. 10 is in the set, but 12 is not, and 14 is the last element of the complement of C. So this is what C complement is: 2, 6, 10, 14. Okay. So here are two useful tools that we're going to show you. These are called De Morgan's laws. Okay, so the first one says that A union B complement is equal to A complement intersect B complement. And the second one says that A intersect B complement equals A complement union B complement. I'm not going to prove these, but if you wanted to, you could prove them. They're not exceptionally hard. But these tools will let us do some extra union and complement problems. So let's take a look at how about A intersect D complement. So here, this problem here, we could find the things that are in A and then find the things that are in D and then take the complement. Or we can use De Morgan's law to say that this is the same as A complement union D complement. And so from here, we need to look at what is in A and what is in D, and we'll take the complements of each and then take the union. So the complement of A is equal to the complement of A. Well, A was equal to it was the set 2, 4. So the complement of A is going to be 6, 8, 10, 12, 14. And the complement of D is equal to, D were the numbers 2, 6, and 10, so the complement is going to be 4, 8, 12, and 14. And so the union, which is what we were looking for in the first place, is going to be 6. The order doesn't matter, but I like to put them in order. So here's a 4, here's a 6, here's an 8, here's a 10, here's a 12, here's a 14. 8, 10, 12, 14. There we go. So that wasn't so bad. Now sometimes we, as we're doing this, it's easier to do our union and then our intersection, and sometimes it's easier to use De Morgan's law and then calculate out our set. That will vary according to context. It probably wasn't easier to use De Morgan's law in this example, but we just chose to, just to show it off. Okay, so let's pull up another question. Let's see. Oh, this one might be a little tricky. We're going to do a proof. This proof might be a little tough, but we will get through it. We're going to prove this. A intersect B union A intersect B complement equals A. Now, this would be something that you might do in a proofs class and at a university. I mean, in the first few weeks of class. It's not typically a question that would be asked for like a calculus student or a finite math student or a business math student, but it's not so bad, really, and it kind of gives you the flavor of what a proof might look like. So the way to show that two sets are equal is you have to show that one set is in the other, and vice versa. The other set is in the first. And the way you do that is you show that if you had an element in one set, it would end up being in the other, and then vice versa. So we're first going to show that if X is in the left-hand side, then X is in A. This is the forward direction of the proof, is what we call it. Then, after we do the forward direction of the proof, we have to do the reverse direction, showing that if it's in A, it's in this thing. Okay, so let X be an element of A intersect B union A intersect B inverse. Then X exists in, well, if X is in the union, then X has to exist in one of these. So X is in A intersect B, or X is in A intersect B complement. That's what it means to be a union. But, so let's say X is in the first. Let's say X is in A intersect B. Well, then it's in A, because to be in the intersection, you have to be in both. Now let's look at the other one. If X is in this one, then X is in A, and it's in B complement. So it still has to be in A. So either X is in A intersect B, in which case it's in A, or it's in A intersect B complement, in which case it's in A. And either way, X is in A. And that is the forward proof. And then the reverse proof, we show the other way around. This is the symbol for the reverse part of a proof. This time, we want to show that if it's in A, then it's in this set. Okay. So first we let X be an element of A. Then X in B or X in B complement. It's either in one or the other. That's part of the definitions of set theory, is every element is either in the set or not. So whichever is true, it's one of these has to be true. Either X is in B or X is not in B. Well, what does that mean? If the first is true, then X exists in A and X exists in B. So X exists in the intersection. Or, let's say that X is not in B. Then X is in A and X is in B complement. So X exists in A intersect B complement. So X has to be in one of these. But if I'm in one of these, then I'm in the union, because the union is all of the things that are in at least one of the sets. So X exists in A intersect B union A intersect B complement. And that's the end of the reverse proof. So we proved that these two sets are in fact equal. Okay. Let's move on to our next question of the day. So that was probably a stretching question, one that shows if we really have mastered what set theory looks like. Ooh, so here is another question. So, here's another thing that we can learn. Elements of a set can be sets. So let's look at this. I think I'm going to call this question 4 for the day. We're going to start with a set. A equals the set containing 1, 2, 3, the set containing 3, and the set containing 1, 4, and 7. So that looks a little tricky. But it's not so bad. It just means that A has 5 elements in it. 1, 2, 3. This is our 4th element. And this is our 5th element. This 5th element is a set that contains 3 numbers. The 4th element is a set that contains 1 number. And I guess the first question you might have is, what's the difference between containing 3 and containing the set containing 3? That's not a bad question. Here's the difference. The set A contains 3 means that 3 is in A. A contains the set containing 3 means that it's kind of like if 3 is a shirt. A is a suitcase that has a shirt inside of it. But A also has, A is also a suitcase that has inside of it a suitcase that has a shirt in it. Sets are like suitcases. You can put stuff in them. And if you have a set inside of your set, it's kind of like having a suitcase inside of a suitcase. And so what we have here is A is kind of like a suitcase that has a shirt in it, but also has a suitcase that has a shirt in it. A is a suitcase with a shirt and a suitcase with a shirt. So that might seem a little strange, but that's one way to think of it. Is you can have a box that has a box inside of it. So you can have a box that has a 3 in it, but next to that 3 there is another box with another 3 inside of it. That's what the set kind of looks like. Okay, so let us look at some statements and see if they're true or false. So 1 is an element of A. 4 is an element of A. The set containing 2 is an element of A. The set containing 3 is an element of A. The set containing 3 is an element of A. So I have these 5 statements, and I want to figure out which of these statements are true and which are false. Is 1 in A? Yes, it is right there. 1 is in A. This is true. Is 4 in A? The answer is no. 4 is in this set, and this set is in A, but the element 4 is actually not directly in A. 4 is in something that is in A, but 4 is not directly in A. Is the set containing 2 in A? The same reason, no. 2 is in A, but a suitcase containing 2 is not in A. A set containing 2 is not in A. Likewise, the set containing 3 is in A, but the set containing a set containing 3 is not in A. This is a suitcase that has nothing in it but a suitcase that has a 3 in it. That's not in A. And the last one, the set containing 3 is in A. That is correct. This is in A, so this statement is true. Great. So, we have time for one more set theory question, and tomorrow I think we'll move on to probability, including Bayes' theorem. So that's what we're going to do our live stream on tomorrow. Of course, email your questions to me, and I will add them to the list of questions to go over. So let us do one more set question. Something that we haven't really done in these videos, I think, are power series questions, or power set questions. Okay, so let us remember what a power set is, and then figure out how many elements are in the power set of a particular set. So I have a set. I'm going to call this question 5 for today. I forget what we're actually on, but we have a set A, and it's going to contain number 1, number 2, and number 3 in it. Now the power set of A is usually marked P of A, or whatever set we're using. If we have set X, then it's the power set of X is marked P of X, and it's equal to, it's the set containing every subset of A. So, of course, every set has the empty set in it as a subset. This set has the set containing 1 as a subset, the set containing 2 as a subset, the set containing 3 as a subset, the set containing 1 and 2 as a subset, the set containing 2 and 3 as a subset, the set containing 1 and 3 as a subset, and A. Every set is a subset of itself, so A is a subset of A. And we see, well, how many elements are there in the power set? 1, 2, 3, 4, 5, 6, 7, 8. So the number of elements in the power set of A is equal to 8. So, and in general, the number of elements in the power set of a set X is equal to 2 to the number of elements in the set X. So, if we have 3 elements in our set, like A has 3 elements here, then the number of elements of the power set is 2 to the third, or 8. If we have some other number of elements, that'd be the number of elements in X is our exponent. The number of elements in the power set is 2 to that exponent. And that's where we're going to leave off our live stream today. So, thank you for watching the live stream. I hope that you're having a great time learning about set theory and finite math and probability. And if you're one of our calculus listeners, I hope you're enjoying learning calculus. And please send me your questions, all of you, so that I can answer them in tomorrow's live stream. See you tomorrow at 5 o'clock Mountain Daylight Time. And bye, YouTube land.